In this video, we work through a position velocity acceleration problem where we're given the position of a person walking back and forth on the t-axis, or excuse me, the x-axis as a function of time. It's given by this graph. I'm going to graph this on my paper with you, and then we will come up with an equation representing this piecewise function, excuse me, and then we can talk about the motion of somebody traveling with a position that's given by this piecewise function. Okay, so this is our x is a function of time. This is the time axis. This is our position. Now this is a one-dimensional motion problem. It's a one-dimensional axis. Because basically this x position is just motion back and forth on some straight line. And this is telling us our position at some given value of time, assuming that we start at time t equals 0. Now, we notice that from this curve, at time t equals 0, our person is at location x equals 0, because when t equals 0, x equals 0, it meets here at the origin. So here's x equals 0. And then at time t equals 2, our person is at location x equals 4. So maybe this is, maybe x is in meters. Let's say that that's 0 meters from where we started, and this is 1 meter, 2 meters. 3 meters and 4 meters. So at time t equals 2, our person is over here. And then from t equals 4 to t equals 7, our person is at x equals 6. And I'll write that interval of values. So t is between 4 and 7. And then at t equals 10, our person is at position or as at x value of -3. So if this is the x equals 0 point, the person is over here at t equals 10. And I guess we could have added some extra points. At t equals 8, the person is back here. And then at t equals 9, the person is back at 0. And then at t equals 12 seconds, the person is at t equals 1. Maybe I should go through that again. Okay, so let's assume that time is in seconds, just so that should we do seconds? Let's just do seconds. And that x is measured in meters. This is giving us positions as a function of time. So t equals 0, we're here. 2, we're here. 4 through 7, we're here. 8, we're here. 10, we're here. And then 9, we're here. And then at t equals 12 seconds, we're here. So you can imagine this guy is just moving. This person's moving back and forth on the x-axis. And we'd like to sort of find a piecewise function representing this curve, or find an equation for the piecewise function in our picture. And then we can calculate the velocity, and we can look at that graph and talk about what that means for our person that's moving along this x-axis. So for this part, I noticed that I've got part of a parabola. And I know it's a parabola because if I start here at 0, 0, and I go to the right 1 unit and up 1 unit, and the right 2 units and up 4 units, that's giving me part of the graph of y equals x squared, or if our independent variable is t, that's x of t in this case equals t squared. But we don't get the whole thing. We just get that part of the parabola that's on this piece, on this interval of values where t is between 0 and 2 seconds. So our position as a function of time is given by t squared, where t is between 0 and 2. There we go. And then on this piece, we notice that it's linear. Now, I increase my x values by 2, and my x values by 2 when I increase my t values by 2. So the change in x divided by change in time is just 1 divided by 1. So that's a line segment with a slope of 1. And then if we just imagine going backwards there, we can see that that line segment would intersect the x of t axis at t equals 2, or excuse me, at x equals 2. So we would have the function x of t is t plus 2, but only on this interval from t equals 2 seconds to t equals 4 seconds. And then on the interval from 4 to 7, the function is just a constant, it's just 6. And then on this piece, it's just a line, so we just need to find the slope of the line. Here we go down 3 units. So we're starting at x equals 6, we're going down 3 in the x direction, and then to the right 1 unit in the t direction. So we go down 3 and over 1, so the slope is -3. And I notice that my function passes through this point. When x equals 9, my function is equal to 0. So this must be -3 times t. When x equals 9, I would have -27 there. So I'm going to add 27 to make sure that when t equals 9, I get 0. So this was from t equals 4 to 7. This is from t equals 7 to t equals 10. And then on the interval from 10 to 12, we get another piece of a parabola, but it's been shifted a little bit. The vertex, so that's that lowest point on the parabola, still occurs at the point that we're starting at. We started here and then we go up 1 and over 1 and then up 3 and over 1. So it looks like t squared, but we've changed the vertex. The vertex is at 10, -3. So I'm just going to take t and I'm going to subtract 10. I'll square that. Subtracting the 10 moves that vertex t units to the right, or 10 units to the right. And then to move it down in the x direction, I'm going to subtract 3. And that's for t between 10 and 12. And I chose these values just because I was trying to come up with a simple curve, a simple function, where sometimes we would have something quadratic. Occasionally, or most of the time, we would have a function that's linear. And I wanted to use transformations and I wanted the function to be continuous. So that the person didn't just like jump from one location to another at a particular time. Like I want that person to be walking back and forth on an axis in a continuous way. Now, all these pieces are joined. It's continuous. I can draw the entire curve without picking up my function. So these intervals need to include 4, 7, 10. I'm just going to put less than or equal to signs on this side. Because it's continuous, I could have just as easily put less than or equal to signs on these guys, but it's tradition to usually use a less than or equal to on the first part. And then the function is continuous at t equals 12, so we'll put less than or equal to there as well. So this is our x of t. Now our velocity is given by x prime of t. So if we want to, we can just compute those derivatives for each of those pieces by computing the derivative, just using our basic derivative rules. Now, one of our derivative rules was that the derivative with respect to x of x to the n is n times x to the n minus 1. So it's called the power rule. If you have a variable raised to some power and you're differentiating with respect to that variable, then we just bring the power down, multiply by that variable to the 1 less power. We're going to use the same thing here, but there's a t instead of an x. Same rule applies. So we'll bring the 2 down, then multiply by t to the 1 less power. And that's going to be the derivative on the interval from 0 to 2. Now, we say that a function has a derivative from the right if the limit if the slope is well defined as we approach that point from the right. And our slope is well defined and our curve was continuous there. So we can actually include this point when t equals 0. We have a tendency when we're computing the derivative to include the endpoints, provided the derivatives actually are well defined there, as if we were to continue that curve, because if the graph we're continuing on the other side. We know that the derivative would have been 0 for t squared. And here, we're gonna have a derivative that's well-defined for that point on the parabola as well. So we can include that on the left endpoint and the right endpoint, but we don't tend to do that at these other points unless it's very smooth, unless you have the same limit from the left and the right. Now in this piece, the function is linear. We have the derivative of a or t plus a constant. The derivative of a constant times t is just the constant, so we get 1. And the derivative of that constant is 0. And that makes sense because the slope of this line segment is 1. We go up 2 and over 2. That's on the interval from t equals 2 to 4. And then on the interval from t equals 4 to t equals 7, the function is just 6. It doesn't change. So the rate of change is 0. And then on this piece, well, the rate of change is just found by using rise over run or fall over run. We go down 3 and over 1. So the slope is -3. That's for the interval from t equals 7 to t equals 10. Again, I'm thinking of t as in seconds. So from t equals 7 to t equals 10 seconds, our slope is -3. And our on this piece, we can take the derivative using the chain rule. If we wanted to, we could write this twice FOIL and then just take the derivative piece by piece. But we know the chain rule now, so we can apply the chain rule here. This is our inside function. The outside function is the squaring function. The derivative of a function squared is 2 times the original function times the derivative of the inside, which in this case is 1. And minus the derivative of 3, which is 0, on the interval from 10 to 12. And we will include that endpoint because the slope is well defined at t equals 12. At t equals 12, the slope is just 12 minus 2, which is 10 times 2. So it's going to be 20. It's going to be a slope of 20. And if this is in meters, if x is in meters and this is in seconds, our slope, remember, can be written also as dx dt, is the change in meters per unit time, or it's going to be given in meters per second. So now let's graph that. Now you might graph that on a new set of axes, but typically on a quiz or a test, I would just give you this grid and ask you to graph x prime and x double prime. The derivative of this t squared was 2t. So we start at the origin, we go up 2 and over 1, up 2 and over 1. Oops. Oops, that should be straight. And then we've got an open circle at t equals 2. And then on the interval from 2 to 4, our derivative value is 1. So just draw a horizontal line with a slope of 1. And then on the interval from 4 to 7, our slope was 0. So I would graph y equals 0, which is the t-axis, or x equals 0. Actually, it's x prime equals 0 now. From 4 to 7, we get a 0 as our slope. And then from 7 to 10, the slope is -3. And then on this piece, our slope is 2 times the quantity t minus 2. Or if we want, we can distribute that. This is 2t minus 4. The way I have a tendency to graph this is to just substitute t equals 10. When t equals 10, I'm going to have 20 minus 4, which is 16. Oh, goodness. That can't be right. The slope is supposed to be 0 there. Oh, the inside function was 10, not 2. Do. When t equals 10, we get, that's better. This is 2 times the quantity t minus 10. If I distribute the 2, I get 2t minus 20. I have a slope of 0. And then at t equals 12, we're going to have 12 minus 10, which is 2, times 2 is 4. And we know that the function is linear. This is just a line in the plane where t is our independent variable. So I'm just going to draw a line segment between those two. Okay, so this is not the best graph. It's a little bit difficult to see, having some issues with my camera. But I think that you can see that if my graph is a parabola, that the derivative should be a line. And anytime it's just a line, the derivative should be a horizontal line. And that horizontal line's value should be the value of the slope. But again, how do we interpret this? We're just saying on the interval from t equals 0 to 2 seconds, our velocity in meters per second is given by 2t. So at t equals 0, our velocity is 0, and at t equals 1, our velocity is 2 times 1, which is 2, and at t equals 2, our velocity is 2 times 4, or excuse me, 2 times 2, which is 4. And so we get this, and then we have sort of a sharp corner. At this point, our velocity changes from this 2t to just a velocity of 1 meter per second. So imagine we're just moving at 1 meter per second the whole time. And then from here to here, we're not moving at all. The velocity is 0 meters per second. So the person's just standing still. And then from t equals 7 to t equals 10, our velocity is 3 meters per second. So our speed is actually 3 meters per second. But because it's negative, we're going backwards. We're going in the opposite direction. And then at t equals 10, our speed starts at 0, and then it goes all the way up to 4. So let's look at our little person here. I think I'm going to highlight those parts where he's moving forwards versus where he's moving backwards. So at t equals 0, we're here. And then at t equals 2, we're over at this location. So at t equals 0, we're there. At t equals 1, we're at 1. And then at t equals 2, we're at 4. So we're actually speeding up. Our velocity is increasing as we're going from here to here. And then at t equals 4, we're at location 6. So we're 6 meters along the x-axis. So you imagine this person, he's walking, and he speeds up, he speeds up, he speeds up. And then he starts walking at a constant speed of 1 meter per second from 4 meters from where he started to 6 meters from where he started. And then for 3 seconds, he just hangs out there. He just stands there for 3 seconds. And then at this point, after standing there for 3 seconds, well, then he turns around because our velocity is negative. He starts going in the opposite direction. So at t equals 8 seconds, he's no longer over here. He's over here at x equals 3. So he's turned around from t equals 7 to t equals 8. And he starts walking the other way. I'm going to highlight the person in blue when they start walking in the opposite direction. And then at t equals 9, he's back at the origin. And then at t equals 10, he's at t equals -3. Now the whole time from t equals 7 to t equals 8 to t equals 9 to t equals 10, notice that that spacing is even. He's walking at a constant speed of -3 meters per second. So every second, he's going backwards 3 meters from where he was. He was at 6 meters, then he goes backwards 3 to 3 meters, then he goes backwards 3 to 0 meters, then he goes backwards 3 to -3 meters, but he's walking at a constant speed of -3. And then at that point, when he's at t equals 10, then he starts speeding up and he goes in the opposite direction. So at t equals 11, where does he end up? He's at t equals -2. So he's going to be back at this location at t equals 11. And then at t equals 12, he's continuing to speed up and he ends up at this location. So it goes from here to here in 1 second, and then from here to here in another second. So he starts to go, and then he goes really fast from there to there. He goes 1 unit in 1 second, and then he goes 3 units in 1 second. And that change in the speed, or that speed, excuse me, the velocity, is described by this 2 times the quantity t minus 10, or if we distribute to t minus 20. So I hope that helps. I hope you can see that when the velocity is positive, we're moving in this direction. And when the velocity is negative, we're moving in the opposite direction. When that velocity is something other than a constant, the function or the person is actually speeding up. So from t equals 0 to t equals 2, he's speeding up. He's going from here all the way to here. And then from t equals 10 to t equals 12, he's also speeding up. He's going from here to here, very close, and his speed just keeps increasing. But on each of these linear pieces, on these piecewise constant pieces, the person is moving at a constant speed. He's dropping 3 meters, he's dropping 3 meters, he's dropping 3 meters on this piece. T equals 4 to 7, he just stands there, he does nothing. And then from t equals 2 to t equals 4, well, we start at t equals 4, I don't think I drew that. Or excuse me, t equals 2. At t equals 2, he's at location x equals 4 meters along our axis. And then 2 seconds later, he's at location 6. So he's going 1 meter per second from t equals 2 to t equals 4. So I hope that helps. I hope that you understand what this graph represents. Now, if we wanted to, we could also graph the speed. So this is the velocity, and but the speed is going to look very similar. The speed is going to be the same as the velocity whenever the velocity is positive. So it's going to be the same as the velocity here and here and here and here, but it's going to be the opposite of the velocity when the velocity is negative. So on this piece, our velocity was -3. So when I graph the speed, it's going to look the same as this one, except on this interval from 7 to 10, I'm going to graph my speed up here. But otherwise, it's exactly the same. It's the same as the original function value. So this is, our speed is increasing. This is our speed is constant at a speed of 1. We're not moving at all, so speed is 0. Here, speed is 3 meters per second, but we're moving in the opposite direction. And then here, our speed is increasing again. We start at 0, and then we go to a speed of 4 meters per second. So now you might say, okay, well, what does the acceleration look like? The acceleration is the derivative of velocity. So we can find the acceleration by computing the derivative of velocity. Or if you want, you could compute the second derivative of position. Either one would be fine. The derivative of 2t, just a constant times t is just our constant. So we're going to get 2 on the interval from 0 to 2. On each of these pieces, the function is constant. So its derivative is 0. But you want to be careful. These endpoints are not included for our velocity graph, so they're not going to be included in our acceleration graph. So from t equals 2 to 10, our velocity would have been 0, but we have to exclude t equals 4 and t equals 7 because our velocity is not well defined there. And then on this piece, the velocity is just 2 again. If you wanted, you could just add another interval there, but I'll add a third branch to my acceleration function. And so we get that. So if I want to graph that on this set of axes, I can graph that. Whoa, I lost my paper. So our acceleration, which we can denote by x double prime, it's going to be a number of meters per second squared. We'd abbreviate this meters per second squared, and this one meters per second. Since we just use meters, just an m. The slope of this line segment is just 2. And then this slope is going to be 0. And this slope is going to be 0. And this slope is 0. So I'm thinking in terms of slope when I graph the derivative. And then the slope of this piece is also 2. But then when I interpret it, I'm thinking in terms of motion. So we say our acceleration is 2 meters per second squared on this interval from t equals 0 to t equals 2 seconds. So when our person is starting at this location and then ending at this location, they go from here to here to here. So they're speeding up. So every 1 second, the velocity of that person is increasing by 2 meters per second. Does that make sense? Every second, the velocity increases by 2 meters per second. So 2 meters per second squared, yes. I think that's correct. And then on each of these pieces, the velocity or the derivative of the velocity is 0. So the velocity actually isn't changing. We're moving at a constant speed of 1 here and a constant speed of 0, which means we're not moving, and then a constant speed of or 3, or velocity of -3. So we're imagining that person is just from here and here and here and here. It's very difficult to walk at a constant speed, but that's what this graph suggests. And then from t equals 10 to t equals 12 seconds, we're starting at this location again at x equals -3 meters. And then we go over here to x equals 12 meters. We go from the -3 to the -2 at that location to this one over here. So we start here, then we're here, and then we're here. The person is speeding up. And the speed is increasing. So our acceleration is this 2 meters per second. So every second, the velocity is increasing by a meter or 2 meters per second. Or does that make sense? 2 meters per second. So that's what a meter per second squared is. It's meters per second per second. Okay. So you might ask, okay, when is the person speeding up? When is the person slowing down? Speeding up, we have a tendency to think of accelerating. The speed or the velocity is increasing. Speed and velocity are increasing on this interval from 0 to 2. And then the velocity is constant here and here and here. That's from t equals 2 to 4, t equals 4 to 7, and t equals 7 to 10. Or if you want, you can use interval notation. Same thing. And then are we ever slowing down? I don't think so. We're speeding up here as well. Speeding up on the interval from 0 to 2, and then again on the interval from 10 to 12. We start it with a constant speed of 0 at that location, and then our speed increases from 0 to 4. So we're accelerating there in that interval. So it doesn't happen on this interval. Or it doesn't happen, say, in the interval from 0 to 12 seconds. Okay, so that's how I would describe the person's motion on each of those intervals. Now, you might say, is this realistic? Probably not. Do we move from having an acceleration of 2 to having a 0 acceleration all of a sudden? Do we go from speeding up to suddenly going at a constant velocity? Well, yeah, I mean, we can do that. Like we can speed up, like when we start our car, we start to speed up, and then eventually, you can put cruise control on and go at a constant velocity of some particular number of, kilometers per hour, for example. But so maybe this isn't necessarily realistic, but we see we're speeding up, then we have constant velocity. We're talking about a person that's walking back and forth, so this is a little bit different than that. But the idea is the same. The person is speeding up as they go from x equals 0 to x equals 4. And then they move with a constant velocity from 4 to 6. So traveling the same number of units in the x direction every second. And then from 4 to 6, or 4 to 7, they just stand there. And then from t equals 7 to t equals 8, or t equals 7 to 10, they move with a constant velocity or constant speed of 3 meters per second, but they go backwards. And then on this interval, they're at this location and they start to speed up. So they go from here and from here to here in 1 second, and then from here to here in another second. So are not going very fast at first, but then they start going really fast on in the next second later. So I hope that helps. Let's actually graph all of this on Desmos. We'll see what the graph looks like, but it's going to be the same as what we've drawn on the paper. Okay, so I'm going to graph my piecewise function for the derivative. I've actually already typed those functions in down here, but I'm going to retype them for us just so that we can think through the derivative again. The derivative of t squared is 2t. Now, sometimes the prime notation works in Desmos, sometimes it doesn't. This time it's not working. It's not automatically taking the derivative for me. So I'm just going to call that x sub 1 prime of t, and that's 2t. But again, I'm only interested in it being 2t on the interval from 0 to 2. We'll include that endpoint because of the convention that we include the limits from the left and limits from the right on the endpoints of our graph. And remember, derivatives are limits. So we have that. And then on this interval, the derivative of t plus 2 with respect to t is just 1. Now, all of these look like separate functions, but that's just because of the way Desmos sort of sets it up. You know, we don't want to, or at least I don't know how to do the piecewise function in Desmos without defining the function on various pieces. So I'm calling this x sub 1 for the first piece, x sub 2 for the second piece, x sub 3 for the third, and so on. But the derivative of t plus 1 with respect to t is just 1. And again, that's just on the interval from 2 to 4. So I'll graph that. And then the derivative of the third piece, the derivative of this piece is 0. And that's on the interval from 4 to 7. And then on the interval from 7 to 10, we have the derivative of this quantity right here. Now, this might be interesting to you. The way I came up with this equation was the same way that I come up with the equation of the tangent line. So I wanted a line that passed through the point x equals 7, y equals 6. With a slope of -3. So I just typed -3 times the quantity t minus the x value that I was interested in. So I wanted it to pass through 7, 6. So I typed in t minus 7. That would have crossed the t-axis at t equals 7. So it would have been way down here. So in order to make it pass through at 6, I just add 6 to it, and it puts the graph where I want it. Now, in order to take the derivative, I would usually tend to at least think through distributing that -3. I get -3t plus 21 plus 6, -3t plus 27. We can also find the y-intercept of that function just by thinking through, well, what would the constant have to be to give me a function value of 0 when t equals 9? And so that's what we did on paper. But so on the fourth piece, our derivative is -3. Again, we're just interested on the interval from 3 to 10 there. And I want these all to be the same color, so let's make them all purple. And then for x sub 5, which is just the fifth piece of my piecewise function, I have the derivative of this expression. And that was 2 times the quantity t minus 10. So it's 2 times the inside function, which is t minus 10, times the derivative of the inside, which is 1. So if we distribute the 2, we get 2t minus 20. That's just on the interval from 10 to 12. And we have a tendency to include that left endpoint, or excuse me, the right endpoint in this case. So I type less than or equal to. And we get that. And I had made them all purple this time. And then I want open circles at different locations. Actually, I think I made them green when I first created this. Because the derivative is not well defined at any of those points where that we have like a sharp corner. Where the slope from the left and the slope from the right are not the same. Actually, it would be easier to see if I graphed these. And get rid of the original points on the graph. But now we see the green function and then the original function are sort of side by side there. And I've got this piece. Looks like I made a mistake somewhere. Yeah, this isn't correct. Slope is 0 there, so it should be this one. And that means the point 10, 0 needs to be on our graph as well. It is an open circle. And we see now the original graph and then its derivative. If we wanted to, we could get rid of the original graph. Just to make it a little clearer what the derivative function looks like. And again, this is now, instead of being, oops. I want to get rid of that point as well. That's t equals 12. When t equals 12, x equals 1. It's not correct. When t equals 12, the velocity is approaching 4. Okay, so that's our derivative. And of course, this slope is 2, this slope is 2, and all of these slopes are 0. So we can type that in over here and then graph that as well. So again, I just typed those derivatives because Desmos was giving me problems with the computing the derivatives. I just typed double prime as part of the subscript for each of those. So the function slope was 2 here and 2 here, and then it was 0 everywhere else. And everywhere where our original first derivative was discontinuous, we have some holes that limit points from the left and right that the function or the derivative function approaches. And if we get rid of the original derivative and the corresponding points, makes it a little bit easier to see the second derivative. Oops, and there's some extra pieces in there. So now we have the first derivative in there twice. But yeah, that's the second derivative. Acceleration of 2 on this interval and this interval and 0 everywhere else with open circles at all the points of discontinuity of the first derivative. Now in this case, we should actually change our label. I would call this x double prime. Or if we wanted, we could call it a of t for acceleration. So that's the acceleration as a function of time. The other one we would type v of t for velocity as a function of time. And if you want to graph the speed, you just take the absolute value of velocity. So everywhere where the function is positive, it stays the same. When anywhere, any intervals where the function is negative, you multiply by a -1 to make it positive. All right, I think that's it. Let me know if you have any questions.